morning. Today we have the lecture entitled Robotics Primer, where we focus on kinematics and dynamics of robotic systems. The outline of this lecture will be: first we will discuss on robot kinematics. In that we will be seeing both forward kinematics with examples and inverse kinematics with examples. Then we see the dynamics of a robotic system. In that again we see the classification of dynamics, which is forward dynamics and inverse dynamics, along with the model based robot dynamic control. Coming to the kinematics, what is kinematics? Kinematics is a study of motion considering the relationship between the robot joints and the Cartesian positions reached by the robotic system. It is classified into forward kinematics and inverse kinematics. In forward kinematics, we have the inputs being the joint angles and the output being the end effector position. So, there is only one to one relationship. You give the joint angle, definitely it will go to one position. Whereas, in the case of inverse kinematics, we have the input being the end effector position and the output of the inverse kinematics is the joint angles. So, having seen the description of forward kinematics and inverse kinematics, we can say that forward kinematics is simpler as compared to that of the inverse kinematics. For the control of robotic system, inverse kinematic can be used. Now, let us go deep into forward kinematics. As seen from the schematic, you can see that Q, general coordinate of the robotic system, it has 3-link robotic system. For that we have the joint variables theta 1, theta 2, theta 3. So, here as I mentioned, we provide some joint angle and it reaches here. That means it was earlier lying here, this robotic system L1, L2, L3, and once we give theta 1, theta 2, theta 3, this one comes here to position A. Now, for forward kinematics, the important analysis that we have to do is through DH parameters, Denavit and Hartenberg parameters. They are 4 in numbers. One is AI, DI, theta I and alpha I. As the name indicates, AI, DI are the link lengths or precisely the length parameters, and alpha I, theta I are the angular parameters. When we say AI, let us define that. What is AI? AI is the distance along xi from OI to the intersection of xi and zi minus 1 axis. Similarly, DI is the distance along zi minus 1 from OI minus 1 to the intersection of xi and zi minus 1 axis. Di is the variable if the joint I is prismatic, whereas in the case of revolute joint, Di can be a constant. Similarly, alpha I is the angle between zi minus 1 and zi measured around zi axis. Finally, theta I is the angle between xi minus 1 and xi axis measured around zi minus 1, and theta I is the variable if the joint I is revolute joint. We can see through the schematics the representation of alpha and theta I. You can see that between zi minus 1 and zi measured around xi, we can get alpha I, whereas in the case of theta I, the theta I is the angle around zi minus 1 between zi minus 1 and xi. So, now theta 4 is an angle around z3. Similarly, theta 9 is an angle around z8, okay, between axis x8 and x9. In forward kinematics, through the DH parameters, we must need to have the homogeneous transformation matrix, which is given by a combination of rotation, translation and rotation, which means it is a combination of rotation and translation. More accurately, it is first having the rotation around z axis by an amount theta I, then translation along z axis by an amount di, then translation along x axis by an amount ai, and finally rotation around x axis by an amount alpha I. With this combination we can get the homogeneous transformation 4 cross 4 matrix. Okay. So, finally, having substituted what is rotation around z axis by theta, and similarly for translation and rotation along around x axis, we have this for these 4 matrices combinedly they form this one, the final matrix, where the last row 0 0 0 1 is the scale value that will help us in having the analysis based on DH parameters in order to have for n degrees of freedom robotic system, in order to have the position and orientation of the end effector with respect to the base, or the position and orientation of the nth frame with respect to the 0th or base frame, we can have the simplification that is aided by this scalar term or the scalar row placed in the homogeneous transformation matrix 4th row. Now, we are going to see the algorithm for deriving forward kinematics. First, we need to establish the joint axes of the given manipulator, physical manipulator. What are the joint axes, and term them as z0, z1 up to zn minus 1, and form the base frame such that it obeys the right hand screw rule. Label the origin of the base frame as O0, that means origin O and 0th frame. Locate the origin OI at each joint I, that means joint 1 will have the origin joint O1, joint 3 will have origin O3. Then establish xi along the direction normal to the plane formed by the intersecting z axis zi minus 1 and zi, or along the common normal through OI if the z axes are parallel to each other. That means, if they are parallel, you can have in this way as xi. If they are like this, zi minus 1 and zi, you can have the xi parallel to this plane formed by zi minus 1 and zi. Then form y as per the right hand screw rule at each joint. Now, coming to the example of robot manipulators towards the forward kinematics, we first take a 2 revolute jointed non-planar robotic system, and from 0 to 1 frame we can have the first row of the DH table, and from 1 to 2 frames we can have the second row of the DH table. Finally, we can say that first row contributes to this homogeneous transformation matrix represented by T01, and the second homogeneous transformation matrix for the second row is T12. Finally, T02, that is the position of the tip frame with respect to the base frame 0, is given by the product of these two individual homogeneous transformation matrices. And finally, we get this, from which we can say that the 3 elements of the last column represents the position of the end effector of the robot, and the 3 cross 3 rotational matrix will give the orientation of the end effector, where from the 3 cross 3 we can find alpha, beta and gamma of the end effector. And here we can see the simulation of this non-planar 2 degrees of freedom robotic system. This is basically we have simulated this in MATLAB programming platform. Also, we have done the forward kinematics of a hand exoskeleton developed in our laboratory, which is meant for grasping tasks. And here we can see that in the previous case we have seen kinematics of a serial link. Here it is a kinematic model of a closed loop link, or a closed loop you can say, which is a combination of both physical link or metallic link and the human being link, because the human link is a part of the hand exoskeleton, and hence we have two closed loops coming into picture to form the kinematic model of the hand exoskeleton, and we have tested the kinematic validation. We have first simulated it with the kinematic model that we have made, and then we have validated it. We have moved the real system placed on the human hand and taken the trajectory that we could see that their true trajectories almost matches perfectly, and hence our kinematic model is validated. Now coming to the inverse kinematics, here we have the input is the end effector pose, which means the position and orientation of the end effector, and we need to find the joint variable q, theta and d as the output. That means given a position b in the Cartesian space, we need to move this end effector from position a to b. So at present we have theta 1, theta 2, theta 3 is a joint angular set. We need to find a new joint angular set in order to reach b. So that is the task of inverse kinematics. There are three ways we can do that. One is through direct approach, another one is through geometric approach, and the third one is closed loop inverse kinematics based, which involves the Jacobian matrix computation. The direct or algebraic approach has equating the final value of the end effector pose and orientation, pose and end effector pose matrix, homogeneous matrix with the expression, and by equating it with the nonlinear functions of the joint variables based homogeneous transformation matrices, expressions and the values, we can get the values of theta. The another one is using the geometrical relationship between the joints and the links, that is called geometric approach. Okay, now coming to the closed loop inverse kinematics approach, we can see that the block diagram of the closed loop inverse kinematics approach for inverse kinematics is given here, where given the desired angle or desired position of the Cartesian position of the end effector, we need to have the joint angle formed by this closed loop inverse kinematics, so that the robot tip can reach that xd. So as per the block diagram, we have the first block is the control gain, and then we have the control law, and that law will give q dot, which is the control input to the robotic system, and that is fed back to the robotic system. In terms of simulation, it is the forward kinematic model. In terms of the real system, it will be a robotic system. So the control gain is multiplied by the error and then added to the joint inverse. Okay. So Jacobian inverse. So we can say that q dot equal to j inverse into xd dot plus kp into error. That is a control law, and this control law will lead to first order aerodynamics E dot plus kpe equal to 0. Okay, this differential equation will have the solution E of t, which is going to 0 as time tends to infinity. Okay. So this approach of inverse kinematics ensures that this is point A, point B. You need to reach from point A to point B through various waypoints. So this is the trajectory of the actual robotic system. So this one, this CLIK guarantees that the trajectory between the desired and the actual is 0 almost, because this law, control law, takes into, or the inverse kinematic CLIK law takes into account the error between the Cartesian actual tip position and the Cartesian desired position of the end effector. This is how we get the first order aerodynamic equation. Okay, now coming to the Jacobian matrix. The relationship between the end effector velocities and the joint angular velocities is given by a Jacobian matrix, where the end effector velocity is represented by linear velocity and angular velocity combination, which is equal to j into angular velocity or joint angle velocity. The Jacobian matrix has two components in that. It has two components. One is Jacobian matrix responsible for the position, Jacobian matrix responsible for the orientation. Jacobian matrix is of size in general 6 cross n, where R stands for the row, which is 6 degrees of freedom in the Cartesian space, and n stands for the column, which is the degrees of freedom of the robotic. The n degrees of freedom robotic system will have 6 cross n. So, for a 4 degrees of freedom Scara robot, it will be 6 cross 4 will be the Jacobian matrix. The individual component, each column of a robotic system or a Jacobian matrix is given by JPI and JOI being Zi and 0 vector for a prismatic joint, because the orientation part will be 0 here, whereas for a revolute joint it is Zi minus 1 cross P minus Pi minus 1, where Ci minus 1, Zi minus 1 are the third column of a rotational matrix for I minus 1th frame, and P is the end effector position, and Pi minus 1 is the fourth column of the homogeneous transformation matrix for the frame I minus 1. So, this Jacobian matrix is called geometric Jacobian matrix, where we represented the end effector velocity as x dot equal to 6 cross 1 vector, which is a linear combination of the linear velocities x dot, y dot, z dot, and instead of angle derivative we give the angular velocity as the velocity part. Then we can say that Jacobian matrix is a geometric Jacobian matrix. If we represent the end effector velocity in terms of alpha dot, beta dot, gamma dot, which means the orientation derivative, then we can say that Jacobian involved is analytical Jacobian matrix. Now, the example for inverse kinematics is given for a Scara manipulator which has 4 degrees of freedom. So, when projecting the manipulator's posture onto the xy plane of this Scara manipulator, we get from the 2 revolute jointed robotic system, easily we get a theta 2 joint angle, which is given by this expression, and from this theta 2 we can find theta 1, and then we can go for computing theta 4. Finally, we can find the prismatic joint variable d3 from the above computed joint angles theta 2, theta 1 and theta 4. Okay. Now, coming to the statics, before we enter into dynamics, we just see what is statics. Statics means the study of force considering no motion of the robotic system, whereas we consider only the forces. An object, mobile manipulator is in contact with the wall, so there is no movement, whereas there is force interaction. So, there we will be having statics involved. The goal of statics is to determine the relationship between the generalized forces applied to the end effector and the generalized forces applied to the joints. Forces for a prismatic jointed robotic system and torques for the revolute joints with the manipulator at an equilibrium configuration, and hence the relationship tau equal to J transpose gamma, where gamma is the tip force, tau is the joint torques of the robot. Now, coming to the dynamics. What is dynamics? Dynamics is the study of motion considering the forces associated with the robotic system. Here in this lecture we have seen 3 definitions including dynamics. First one is kinematics. What is kinematics? It is the study of motion considering no forces associated with the robotic system. Then we have the definition of statics, which means the study of forces when there is no movement of the robotic system involved. Then we see dynamics. Dynamics means the study of motion considering the forces associated with the robotic system. The general highly coupled non-linear dynamic equation of a n degrees of freedom robotic system is given by tau equal to m of theta into theta double dot plus v of theta comma theta dot into theta dot plus g of theta, where m is the inertia matrix which is of size n cross n, and v is called Coriolis and centrifugal matrix, which is also n cross n size, and g of theta is gravity vector, which is of size n cross 1, and obviously theta double dot is a joint acceleration vector of size n cross 1, and theta dot is a joint angular velocity of size n cross 1. So, with this we have the left hand side joint torque, which is also of size n cross 1. Now, the dynamics has been classified further into forward dynamics and inverse dynamics. Forward dynamics means the input is torque, that is the input, whereas the output is joint trajectory, theta, double dot, theta dot and theta. Whereas in inverse kinematics, inverse dynamics, we have the input being the joint trajectories and the output will be joint torque. Forward dynamics is used for simulation case, simulation, whereas inverse dynamics is meant for controlling robotic system. Now, having seen that the inverse dynamic model is going to be helpful for controlling robotic system, let us see model based manipulator control system, which means we have a dynamic model given by this expression. If we assume friction also, it becomes one more term, which is friction. Then the model based manipulator control system will have the procedure as such. The first one is we can have the partition control law for this dynamic based robot control given by tau equal to alpha tau dash plus beta. Let that be the partition control law for this case. Again, it is given by tau equal to alpha tau dash plus beta, where tau is the n cross 1 vector of joint torques, and we choose alpha being the mass matrix or the inertia matrix m of theta, and beta being the rest of the dynamic model, which is given by v of theta comma theta dot comma multiplied by theta dot plus g of theta plus f of theta comma theta dot. And we consider the servo law, which is given by tau dash equal to theta d double dot plus kv into e dot plus kp into e, where kp kv are control gain matrices, with e being the difference between desired joint angle and actual joint angle, and e dot being the difference between ed theta d dot minus theta dot. So, now we know the value of alpha, we know what is tau dash and what is beta. So, substituting back into this dynamic model, that means the control law is now substituted back to the dynamic model equation 2, then we can have this second order aerodynamic equation, which is given by E double dot plus kV into E dot plus kp into E equal to 0, which means that the error tends to 0 as time tends to infinity, and the matrices kV and kp are diagonal matrices. So, if we go by joint basis, we have the error vectors coming out to be Ei double dot plus kvi E dot plus kpi E equal to 0. When we have simulated for a given theta d and theta d dot and theta d double dot, we can obtain these values for giving here as input from interpolation. That means take theta naught equal to say 20 degree and theta final being say 45 degree. So, this is your desired angle, and you have one initial angle for the robotic system say 20 degree. Between this and this, you can have an interpolated trajectory from which we can get theta of t, theta dot of t and theta double dot of t, which can be given as input to this case. Thus, in this lecture we have seen robot kinematics, statics and dynamics, with the concluding part as the model based robot dynamic control. As a short, we can say that kinematics involving both forward and inverse kinematics have been seen with examples for both kinematics and forward kinematics and inverse kinematics. As I want to mention that compared to inverse kinematics, forward kinematics is a simpler one. The problem or the challenges associated with inverse kinematics are, in some situation we may get for one position of the end effector we get several or multiple joint angles, and we need to optimize which one is the best joint angle by considering the objective functions to minimize energy or to maximize manipulability measure. Then coming to the statics, we have seen the expression of that, and it is advised by me to read the duality property of robot statics to have the relationship between the end effector forces and the joint torque vector. Then we have seen robot dynamics with forward dynamics and inverse dynamics involved in the model based control. In the model based control, given the input as joint trajectories theta d dot, theta d double dot, we are finding the joint torque vector tau by partition control law given by tau equal to alpha tau dash plus beta, where tau dash is a servo law. Thus, we can involve both forward dynamics and inverse dynamics. Where is forward dynamics involved? Forward dynamics is involved in getting the feedback angles. That means, given the desired joint angle theta d dot and theta d double dot, we can get the actual system's joint variables through forward dynamics, because the forward dynamics receives the joint torque and we get the joint angle by inversing from the dynamic model. Thus, we have seen 3 topics here in the robotics primer involving robot dynamics and robot kinematics. We have seen kinematics, statics and dynamics along with control in this lecture. The readers are requested to go through several books and example problems in order to understand these topics. Thank you very much.